All right, so good afternoon, everyone. We'll discuss the topic of Cohen-Macaulay rings and modules. And Cohen-Macaulay modules. And Cohen-Macaulay will be repeated many times, so I may just write CM for Cohen-Macaulay. The definition will involve the concept of dimension of a module, and it will also involve the concept of regular sequence and the concept of depth. So in this first lecture, I will just focus on properties of regular sequences on modules. So first, let us recall that if R is a commutative ring and M an R module, then X belonging to R is called a non-zero divisor. On M, if you look at the multiplication map from M to M, given by mu x m equal to xm, is injective. Okay, this means that if xm equal to 0 for some m belonging to M, then M is 0. So that's the concept of a non-zero divisor on a module. And the theory of associated primes tells us that if R is Noetherian, if R is a Noetherian ring, if R is a Noetherian ring, then the zero divisors on M, just a minute, I have to change the color. Yeah, the zero divisors on M is the union of associated primes of M. And if M is finitely generated, if it is a finite R module, then this set is a finite set. And we also know that associated primes of M is the variety of annihilator of M, and it is always contained in support of M. Remember, support of M is all prime ideals, so that M localized at P is not equal to 0. So the zero divisors are trapped in the associated primes. So if you want to find a non-zero divisor, you have to look outside the associated primes. Okay. So if, for example, if Rm is a local ring, is a local Noetherian ring, and M a finite R module, and suppose that M is not an associated prime, then M is not contained in the union of associated primes. Yeah, by prime avoidance lemma, M is not contained in the union of associated primes. Yeah, so I can pick an element of M which is not in any associated prime. Okay. So by prime avoidance lemma, there exists an X in M which avoids all the associated primes. And therefore, X is a non-zero divisor on M. Yeah, that's how we find non-zero divisors on modules. They avoid the associated primes. Yeah. So this leads to the concept of regular sequences. So I want to now define these two concepts which are very important. M regular sequence and weak M regular sequence.
Sir, in page 2.
Yeah.
Sir, in page 2, last line, do you intend to mean that M is not a subset of union?
Yeah. That's right. M is not an associate prime, so M is not going to be contained in union of associate primes. Okay. So I can pick an element in M which is not in any associate prime, and that is going to be a non-zero divisor. So that's how we find non-zero divisors. So these two concepts, weak M regular sequence or weak or M regular sequence. Very often word is dropped. Okay, M sequence and weak M sequence, they are synonyms. Okay, so suppose I have a sequence x1, xn. These are elements of R. This is called a weak M sequence.
Sir?
Yeah.
Sir, in the second page, you have written that for M is finite set, means finite module, associated prime is equal to V of annihilator of M.
Yeah.
Sir, is it equality or is it containment?
No, sorry. This is contained in.
And this with support, it should be equality.
Yeah, support it is equal. You are absolutely right. Support, I wanted to say, support is the variety of annihilator, and all associated primes contain the annihilator.
Okay. Okay.
Okay?
Yes, sir.
Yeah. Okay. So x1 up to xn in R, a sequence of elements in R, this is called weak M sequence. If x1 is M, x1 is a non-zero divisor, is a non-zero divisor on M. This is important, non-zero divisor on M. X2 is a non-zero divisor on M mod x1n. X3 is a non-zero divisor on M mod x1, x2n, and so on. Yeah. And xn is a non-zero divisor on M mod x1, x2, xn minus 1m. Yeah, so we go modulo the submodule generated by the previous elements, and then this element xi is a non-zero divisor on M mod the submodule generated by x1 up to xi. Okay, then we say it's a weak M sequence. Yeah, so it is a strengthening of the concept of non-zero divisor to a sequence of elements, and if the submodule generated by these elements is a proper submodule of M, then x1, x2, xn is called an M sequence. Yeah, is the concept clear?
Yes, sir.
Yeah, so let us look at an example. It may take R to be polynomial ring. over a field so this is a domain, so every non-zero element is a non-zero divisor. And so suppose I take the sequence x, y, z, then this generates a maximal ideal. So this times r is not equal to r, yeah. And x is a non-zero divisor, y is a non-zero divisor on r mod xr, yeah, because this is just the domain k, y, z. And z is a non-zero divisor on r mod xyr. So therefore xyz is an M sequence where M is the ring itself. Yeah. So this is true if you take any polynomial ring in finitely many variables x1 up to xn, and then x1 up to xn will be a regular sequence on the ring. Yeah, let us look at slightly different sequence x, y, z. This is the sequence contained in same ring kxyz. And this is a non-zero divisor in the ring. And if I go mod this element, yeah, then what are the associated primes? What are the associated primes of this quotient ring? Can somebody tell me?
X and y minus 1.
Yeah. So you look at this ideal generated by x times y minus 1. This ideal is intersection of x, the ideal principal ideal generated by x and y minus 1. They are prime ideals, and so these are the associate primes. Yeah. So if I look at this element y, this element y is not in any of the associate primes. It's not in x, and it is not a multiple of y minus 1. So y is not in any of the associate prime. And therefore y minus 1 x y is a R sequence. Now let's add this element. Let's look at z times y minus 1. Okay, I want to test whether what is the nature of this element. If I go mod the previous two elements, R over, take the ideal generated by previous two elements.
Sir?
Yeah.
Sir, here y doesn't belong to P, right? For all P in associated primes of R mod xy minus xr.
Right.
So you have written y belongs to.
Yeah,
but
y is not in P. Yeah, y is not in P.
Yeah.
So that's why it is a non-zero divisor. Right? Okay.
Yes, sir.
Now look at this R mod xy minus x over y. This ideal is same as, you see, xy is a multiple of y, so I can just get rid of this. Yeah, this ideal is same as this ideal, and this is same as kz. Yeah, and this z times y minus 1. Therefore, it is non-zero divisor because it's a non-zero element here. I mean, z times y minus 1 is the only associate prime is x comma y of R mod the previous two elements. The only associate prime is x comma y, and z times y minus 1 is not in this ideal. And therefore, x times y minus 1, y, z times y minus 1 is R sequence. Is this clear? Is this clear to everyone?
Yes, sir.
Yeah. But now, so these are three elements, and they turned out to be a regular sequence. X comma y comma z was also a regular sequence. But let me now permute the elements in this second regular sequence. Okay, if you permute last two, yeah, look at this sequence now. Yeah. So is this an R sequence?
So z times y minus 1 will be inside y minus 1.
Right. So when you go mod first element, if you go mod first element, then the associated primes of R mod this are two associated primes, right? This is x and y minus 1. And this element is in this associated prime. So it's a zero divisor. Yeah. So this is not so. So this says that permutation of a R sequence need not be an R sequence. Permutation of an R sequence need not be an R sequence. Yeah. Is this clear? Permutation of an R sequence need not be an R sequence.
So is this the reason behind calling it a sequence?
Pardon?
Is this the reason behind calling it a sequence? Means this ordering matters.
Ordering matters. Yeah, ordering matters. We will see that in many situations, permutation of an R sequence is again an R sequence, but not in general. Even in this best ring, what can be better than polynomial ring? Even in polynomial ring over a field, permutations of regular sequences are not regular sequences. Okay, so that is why it is called a sequence. You are absolutely right. Okay. Okay. Now let's look at another example. Let us see R to be, so let K be a field again, and R equal to, take power series in one variable, yeah, and then take polynomial ring, yeah, right? So I have polynomial ring in one variable over a power series ring in one variable. Okay. Now look at x comma y. This is an R sequence. Yeah, x comma y is a prime ideal of R. If you go mod x comma y, what do you get? X is a non-zero. This is a domain. So x is a non-zero divisor. When you go mod x, I just get ky, which is a domain. And y is a non-zero divisor on R mod x. So x comma y is an R sequence. Is that clear?
Yes, sir.
Now look at 1 minus xy. 1 minus xy. That's a regular element because it's a non-zero divisor, and it is not a invertible. This is not invertible, right? This is a regular element or non-zero divisor. But let's go mod this R mod 1 minus xy. Yeah. So what are you doing? What is this? This is like inverting. This is like inverting x, right? This is like inverting x, putting y equal to 1 over x. If small x and small y are images of big X and big Y in R mod 1 minus xy, then in this ring, xy is equal to 1. So y is equal to 1 over x. So this ring is nothing but R joined, R localized at the multiplicative set, which is generated by x. Yeah. But then what is this? I mean, sorry, this is not R. This is a power series x localized at x. Can you tell me what is this? Can anybody tell me what is this ring? Kx localized at x.
Lorentz series.
Pardon?
Lorentz series. I mean.
Yeah, but do you see that it is a field?
It's because we are inverting the maximal ideal elements, means x, and other elements are already invertible.
Yeah. So this is the quotient field. This is the quotient field of power series ring. Simply by inverting one element, you got the quotient field. That you cannot do that in polynomial ring, right? In polynomial ring, you cannot invert one element and get the quotient field. But in power series ring, yes, quotient field construction is very simple. Just invert x. Okay. Yeah. So therefore, R mod 1 minus xy is a field. So I started with 1 minus xy belonging to my polynomial ring or power series ring. And this, I can't add any further elements to make it a R sequence, right? R sequence, the ideal generated by R sequence should not be the whole ring. That's a condition on R sequence, right? So after going mod 1 minus xy, I got a field. So you can't increase you can't find any more elements to make it a R sequence of length bigger than 1. And so I have two examples. One is this, the x comma y is a maximal R sequence because when I go mod x comma y, I get a field k. Here, if I go mod 1 minus xy, I get a field. So both are maximal R sequences. They can't be extended further. So xy and 1 minus xy are both maximal R sequences. So therefore, maximal R sequences need not have same length. Is that clear? So permutation of R sequence is not an R sequence, and maximal R sequences need not have same length. We will see that if you put further restrictions, some more restrictions on the ring, then maximal R sequences contained in an ideal will have same length. We'll prove that. And I think many of you have already seen a proof in the tutorial that Joydeep offered. Using the extension functors, it was proved that maximal R sequences or maximal M sequences contained in an ideal have same length. And it can be characterized by vanishing of the X modules. And similarly, we will see that permutation of R sequences are R sequences provided they are contained in the maximal ideal of the local ring. If the base ring is a local ring or the sequence is contained in the Jacobson radical, then you can permute in whichever way you like. So these two properties are not true in general, and we will find out the situations where these two properties are actually true. Any questions? You have to go to the correct page. Yeah, 9. All right. So let us examine some more properties. Properties of M sequences and weak M sequences. So remember, M sequence has this condition that, so I will denote by X a sequence X1, X2, Xn. So this is M sequence. Then Xm is not equal to M. Okay. And in weak M sequence, we don't impose this condition. Weak M sequence is just a sequence of elements so that Xi is a non-zero divisor on M mod the submodule generated by X1 up to Xi minus 1. Okay. So let us look at first property, behavior under localization. So let X be a weak M sequence. Okay, it's a weak M sequence, and P is a prime ideal in the support of M. P is a prime ideal in the support of M, and X is contained in P. Then I can look at the sequence X1 over 1, X2 over 1, Xn over 1. Okay, Xi's are in R, so this is in Rp. Okay, this is a sequence which is contained in Rp. In fact, it is contained in PRP. Yeah, Rp is a local ring, and PRP is maximal ideal, and this sequence is contained in PRP. Then this is a weak MP sequence. Okay, this is a MP sequence, right? Because it is contained in PRP, it is a MP sequence. Yeah, so this is due to the fact that localization is exact functor. Localization is exact functor. So just look at those conditions. The conditions for weak sequence, we want to see that Xi, when you take the multiplication map by Xi over 1, yeah, in MP over X1 over 1, xi minus 1 over 1, okay, to the same module. Yeah, this should be injective. Yeah, this should be injective for every I. But I know that mu xi from m to x1 xi minus 1 m to m to x1 xi minus m is injective. And injective maps are preserved under localization. So you just localize at P. To see that mu xi over 1 is injective. And that says that when I go to localization, xn over 1 belonging to P is an MP sequence. Okay, so M sequences or weak M sequences, they are preserved under localization. You will see later, they are, I mean, what property did we use? We simply use that MP is flat over, I mean, when you localize, the localization is localization of a module is flat. Okay, so flatness, flat modules preserved injective maps, and that's what has happened. And later on, when you will study completion of local rings, you will see that completion is also flat over a local ring. It's a flat map from R to R completion, and so that will also preserve M sequences and weak M sequences. Okay. Second property, preservation under tensor product. Or behavior on exact sequences, right? So suppose, so let x be a weak M sequence. So M is any R module, R is a Noetherian ring. You can assume R is commutative in this situation. So we have a weak M sequence, and let N2 to N1 to N0 to M to 0 is an exact sequence of R modules. Then tensor with R mod X, okay, then I get this sequence N2 over Xn2. Yeah, so this X is a sequence, X1, Xn. N1 over Xn1, N0 over Xn0, M over Xn to 0. And this is the map after tensoring with R mod X. Yeah. So if I start with this 4-term exact sequence, which is exact on the right, yeah, and this is an exact sequence, then a tensor with R mod X, then this is exact. Yeah, the assumption is that X is a weak M sequence. X is a weak M sequence. Okay. You will see applications of this in many situations later, especially if you have a free resolution. NIs are free modules, And if I have an element which is M regular as well as the regular on the ring, then I can just tensor with R mod X and again get a exact sequence. And that will give me a free resolution of M mod Xn. Okay, so keep this in mind. I have 4 modules, so it is not a short exact sequence. If N2 is 0, it will become a short exact sequence. So if N2 is 0, then this short exact sequence will be converted into a short exact sequence if X is M weak M sequence. Okay, the short exact sequence is taken to short exact sequence if I tensor with R mod X, where X is a weak M sequence. That's one consequence of this, right? So let us prove this. Is this clear? Any question on the statement? Yeah. So we know that this sequence 2, this sequence 1, 2 is obtained by tensoring 1 by R mod XR. Okay. So, but tensor product is right exact, and therefore this 2 is a right exact sequence. Tensor product is a right exact functor. So hence 2 is a right exact sequence. That means it is exact here, and we have to show exactness here. Yeah, that at this point it is exact. Okay, right exact just means on these last two modules, it is this sequence is exact. That means image of phi 1 bar is kernel of phi 0 bar, and phi 0 bar is surjective. To show that 2 is exact, I need to show that the kernel of phi 0 bar is contained in image of phi 2 bar. Okay, this is exact sequence, so it is a complex. And when I tensor a complex with R mod X, I get another complex. Okay, so image of phi 2 bar is certainly contained in kernel of phi 0 bar, because that is true of this phi 2 and phi 1. But what is not clear is whether the kernel of phi 0 bar is contained in image of phi 2 bar, and that's what we have to show. Is this clear what we have to do to show the exactness of 2, sequence 2? Yeah, we just need to show that image of phi 1 bar is contained in kernel of phi 2 bar. Yeah, or kernel, sorry, other way around. Image of phi 2, sorry, other way around. Kernel of phi 2 bar, kernel of phi 1 bar. Yeah, so I'm trying to prove the exactness at this spot. Okay, so image of phi 2 bar is contained in kernel of phi 0 bar by general principle. So I need to prove the other containment, that the kernel of phi 1 bar is contained in image of phi 2 bar. Okay, so take an element in the kernel of phi 1 bar. So pick an element y bar belonging to kernel of phi 1 bar. Kernel of phi 1 bar is a submodule of n1 over xn1. So this is an element contained in n1 over xn1. Okay. Another remark is that to prove 2 is exact, I may just prove it for n equal to 1 and then do successively. Yeah. So I am assuming that now x is an element, enough to prove when n is 1. So x is x1 now. So pick this element y bar in the kernel of phi 1 bar, which is in n1 over xn1. And so y phi 1 bar of y bar is 0. but this is an element in n0 over xn0, and this is, so this says that phi1 of y is in xn1. So therefore phi1 y equal to some x times, yeah, this is x times some z, where z is an element of n1.
Sir, is it N1 or N0?
N0, sorry, you are right, N0. This is N0 over N0, yeah, N0. Okay, so phi1 y is equal to x times z. So now we have descended to this original sequence. Phi1 y is an element of n0, okay, and it is equal to xz. So if you apply phi0 to it, that is equal to, because it is R linear, phi0 z times x, yeah. But what is the composition of phi0 and phi1? What is this?
0.
That is 0. And where is phi0 z? Phi0 z is in M, right? And x is M regular.
This force is phi 0 z is 0.
Yeah, x is M regular. Implies phi0 z is 0. So z is in the kernel of phi0, but that is image of phi1, and therefore z is equal to phi1 times phi1 of some element. Z is equal to phi1 y prime, where y prime is some element of n1. Okay, so go back to the equation. My equation was phi1 y is xz, and I have found that z is phi1 y prime. So phi1 y is equal to x times phi1 y prime, and therefore phi1 of y minus xy prime is 0. Yeah. So y minus xy prime is in the kernel of phi1, but kernel of phi1 is image of phi2. So therefore, y minus xy prime is equal to phi2 of some y double prime. Yeah. So do you see what has happened now? Now go back to sequence 2. Read this equation in sequence 2. Read this equation in sequence 2. The difference, yeah, y minus xy prime is phi2 y prime, and therefore y bar is equal to phi2 bar y double prime, and that's what we had to prove. Yeah, is this clear? I have proved the exactness of this sequence 2. This sequence 2. I wanted to show that the image kernel of phi1 bar is contained in the image of phi2 bar, and I took this element y bar in the kernel and showed that this y bar is phi2 bar y double prime. So that shows that the kernel of phi1 bar is equal to image of phi2 bar, and therefore the sequence 2 is exact. Yeah, any doubts on this? Okay, now let us prove under what condition permutation of an M sequence is M sequence. In general, this you saw that this is not true. But let us show that if the ring is Noetherian local ring, if Rm is a Noetherian local ring, and M a finite R module, then permutation any permutation of an M sequence in M is again an M sequence. Yeah, so if your M sequence is contained in a maximal ideal of a local Noetherian ring and module is finitely generated, then you can permute and it will still be an M sequence. Okay, let us prove this. So suppose x equal to x1, x2, xn is an M sequence and x is contained in M, the unique maximal ideal of R, and I want to show that any permutation is an M sequence. So let n be equal to 2 first. Let us warm up by proving that if I permute 2 elements in M sequence, it is again an M sequence. See, that was not true in polynomial ring over field in 3 variables. Yeah, but those 3 elements, the ring had lots of maximal ideals. It was not a local ring. So if you take a local ring, then that problem will go away. Okay, that problem will go away. So let us look at 2 elements. So x, y is an M sequence. We want to show that yx is also an M sequence. Yeah. So you see, what is given is that y is a non-zero divisor when I go mod x. Yeah. So x is a non-zero divisor on M, and y is a non-zero divisor on M mod xm. Now I want to show that y is a non-zero divisor on M. Right? We want to show that if ym equal to 0, then M is 0. That will show that this element y is a non-zero divisor on M. Okay. So, but what I know is that y is a non-zero divisor on M mod xm. Okay. So I have this equation. You pass to M mod xm. Pass to M mod xm, then this equation reads in M mod xm, y times M bar equal to 0, where M bar is the residue class. Okay, but y is a non-zero divisor on M mod xm. Okay, y is a non-zero divisor on M mod xm. So this means that M bar is 0 in M mod xm. So M must be equal to some x times n, or x times n, where n is some element of M. Okay. Yeah. Once M is equal to x times n, then see what is y? Y times M is 0. So that is equal to that is equal to yxn, that is equal to 0. Okay. So we started by picking this element m. My was 0, so m belongs to 0 colon y. Yeah. This is a submodule. This is a submodule of m. M is Noetherian module. So this submodule is finitely generated. So this 0 colon y is a finitely generated submodule. And I started by writing my equal to 0. I want to show that m is 0. But I concluded that xyn is 0. Yeah. But if xyn is 0, but I know that this element x is a non-zero divisor on m and yn is an element of n. So yn is also 0. This means yn is also 0. Okay. Yeah. So this element m which I have, I was able to write m as x times n, and this xn turned out to be 0. Yeah. This xn, I mean yn turned out to be 0. This element. Okay. Yeah. So m was in 0 colon y. Okay. But m is also in x times n, and n is also, when multiply n with y, it is also 0. So this is contained in x times 0 colon y. So this says that 0 colon y equal to x times 0 colon y. Yeah, R is a local ring and X is in the maximal ideal. This is a submodule of M, finitely generated. And so 0 colon y is equal to x times 0 colon y. So what can you say about 0 colon y then?
It will be 0 by Nakayama.
Yes.
Right. So by Nakayama lemma implies that this module itself is 0. But m times y is 0. So therefore m is 0. And so y is a non-zero divisor on m. But I need to prove that y comma x is a m sequence. So it remains to show that x is a non-zero divisor on m mod xm. Yeah. But
Sir, m mod ym.
M mod ym. Yeah. M mod ym. But this is relatively easy. This is relatively easy. So pick an element in the annihilator of x. Yeah. So we want to show x is a non-zero divisor. So on m mod ym. So suppose x times m bar is 0, where m bar is an element of m mod ym. So therefore xm is in ym. So xm is equal to ym prime for some m prime in m. Yeah. What can you do now? I know y is the non-zero divisor when I go mod x. So read this equation in m mod xm. Read this in m mod xm. What does it say?
It says y m prime bar is 0.
0.
And y is n by xm regular. So
Right. So
this forces n prime belongs to xm.
m1 belongs to xm. I mean m prime. So, ym m prime bar is 0, so m prime bar is 0, so m1 is in xm, so m1 sorry, I'm mixing up things. So m prime equal to x times some m double prime. Yeah, so go back to this equation and substitute xm equal to ym prime. This is equal to yx m double prime. Now what can you do?
X is a non-zero divisor on M.
Exactly. So
So M equals to ym double prime.
m equal to ym double prime. So what does that show? M bar
M is 0 in M mod
m mod ym. And so x is m mod ym. No. X is m mod ym regular. So yx is an m sequence. Yeah. Is this clear? You see, Nakayama lemma is coming in every lecture, right? You saw it in Professor Patil's lecture. And now it is coming here again. So it's a basic tool. You have to learn to recognize where Nakayama lemma present itself in the proof. Okay. So using that, and Nakayama lemma requires that your module is finitely generated. The ideal is in the Jacobson radical. So using this, we showed that if xy is a m sequence, xy is an m sequence, then x and y are contained in the maximal ideal. So it is an m. If it is an m weak m sequence, didn't put any condition on xm, but the two elements are in the maximal ideal, and therefore xy comma m is not equal to m, right? Because m is not equal to mm. So it is a m sequence. If xy is an m sequence, y comma m is a y comma x is an m sequence. Okay. Yeah. Right. But you see, we wanted to show it for any m sequence, right? So we have proved it for n equal to 2. We have proved it for n equal to 2. Yeah. We want to prove it for arbitrary n. Okay. So now let x1, x2, xn be in m, be an m sequence. And take any permutation. We want to show x pi 1, x pi 2, x pi n is also an m sequence. Yeah. But you see, Sn is generated by transpositions. Sn is generated by transpositions of the type I plus 1. So I can permute two adjacent elements and show that it is an m sequence. Then it will prove that any permutation of an m sequence is also an m sequence. So enough to prove that x1 xi plus 1 xi. Yeah, just permute two adjacent one xn is an m sequence. Is that clear? We just need to prove this special case.
Sir, could you please repeat this?
Any permutation of x1 up to xn can be obtained by permuting adjacent elements, because Sn is generated by such transpositions I comma I plus 1.
Yes, sir.
doing this successively, I can reach any permutation of x1 up to xi. So I just proved that if I exchange adjacent elements in an M sequence, it remains an M sequence.
Okay, sir.
Yeah. So now do you see that it actually follows from n equal to 2 case? Do you see that this is an M sequence?
Yes,
You see?
because this is an M sequence of M by x1 to xi.
Right. So you just look at M mod x1 xi minus 1 M. On this module, this is a M sequence, right? So these two elements form an M sequence on this module. I can interchange them because xy is a regular sequence, yx is also a regular sequence. So xi plus 1 xi is M mod this sequence. Yeah. What will you do now? These two can be permuted. I mean, I permuted them. Xi plus 1 xi is this sequence. Yeah. Now you go mod these two elements. If you go mod two elements, the submodule becomes the same. Okay. So when I look at xi plus 2, then M mod x1 xi plus 1 M. This is anyway this sequence, this regular. And you can go all the way. This is M sequence. This is an M sequence. So we are done. Yeah. Any doubts on this? Okay. Next property. So let 0 to M1 be a sequence of submodules. And x1 xn so here R is any commutative ring. R is a commutative ring, and M is an R module. So suppose I have this sequence, then X is M sequence if and only if X is Mi plus 1 over Mi sequence for all I. So from this filtration of submodules, I can take quotients, and then if you want to test whether a given sequence is an M sequence, I have to just test it on the quotients. Okay, this is extremely useful proposition. If you just test it on the quotients, then it will become a sequence on the big module. The quotients are very often simpler modules, and it is easier to test whether a sequence is a regular sequence on the quotients. Okay. So I have a filtration of H plus 1 modules. I just apply induction on H. You see, most of the proofs about regular sequences are by induction. And there is a natural way to apply induction. Okay. So if H is 1, if H is 1, this is fine. So we should really do see how it goes for H equal to 2. Okay, take H equal to 2. Then I have 0 contained in M1 contained in M2 equal to M. And X is M1 sequence and M sequence. Yeah, I guess I can say weak M sequence. Yeah, weak M sequence. Okay. So M mod M1. Yeah. The first quotient is M1 mod 0. Second quotient is M2 over M1. And X is an M1 sequence, and X is also an M mod M1 sequence. I want to show that X is M sequence. So look at this exact sequence. Okay. Now it is enough to do the n equal to 1 case. Enough to prove n equal to 1 case. Because you can repeatedly apply this and get that, prove the general case. So enough to just go mod 1 element. Yeah. So take this element x1 equal to x. And this element is regular on M1. It is regular on M mod M1. I want to show that it is regular on M. Okay. Yeah. But X is M regular if and only if I take this submodule. What should be this submodule? Annihilator of X. That should be 0, right? Yeah. Now, where do you see annihilator? Annihilator comes as a kernel of which map?
Multiplication by x, m to m.
Right. So I have 0 to M1 to M mod M1. X1 is regular here. And X is regular here. So if I take multiplication by X1 and take multiplication by X1, these are injective maps, right? Okay, these are injective maps. So the kernel is 0 colon X1. Okay, this is a submodule. And here, this is 0 colon X1 on this submodule. And I want to show that the multiplication by X1 is injective here. How do you see that?
Bottom sequence is also exact, and diagrams is like take some non-zero element from M on this.
No, I want you to recall the snake lemma. Snake lemma will say that the kernel, take the kernel of this map, kernel of this map, kernel of this map, then they take the co-kernels, that is a long exact sequence. Kernel of this map is 0 colon X1. And I have obvious map from here to here. And snake lemma says this, and then go to the co-kernel. Take the co-kernel. So call this as M bar over Xn. So the kernel of this map to kernel of this map to kernel of this map to the co-kernel of this map, this is an exact sequence. But this is 0, this is 0, this is 0. Therefore, this is 0. So it says that X1 is regular on M. And moreover, this is an exact sequence. That anyway we proved it earlier. Yeah. Short exact sequence gets converted into short exact sequence after tensing with R mod X if X is regular on the last module in the short exact sequence on the right. Okay. Yeah. So I have proved the statement for h equal to 2 also.
Also, the co-kernel part ensures that m is not equal to xn.
Yeah. The co-kernel part says that x m1 over x1 m is not 0. Are you saying that? You see, the assumption was that x is regular on m1, it is regular on m mod m1. So x times m mod m1 is not m mod m1 by assumption. Okay, so these two modules are non-zero modules, and therefore this is a non-zero module, and so xm is not equal to m, and therefore it is a m sequence.
Yeah.
Yeah, we have to observe that also. So h equal to 2 case is done. Yeah. Now apply induction. Apply induction on h. So let h be bigger than or equal to 3. Yeah. Let h be bigger than or equal to 3. And I have this sequence m1, mh minus 1, mh equal to m. Yeah. The quotients are m1, m2 over m1, mh minus 1 over mh minus 2. So given sequence is a sequence on these modules also. So by induction, x is mh minus 1 sequence. Is it clear? By induction, right? I have a filtration of h minus 1 modules. So x is mh minus 1 sequence. But now look at this short exact sequence. My sequence is sequence on this module. It is a sequence on this module, and so by h equal to 2 case, it is a sequence on this module also, and we are done. Any questions? Is that clear? Okay. We will, for the next property, I need to prove a lemma. So let x equal to x1, xn be m regular sequence. And suppose I have a linear equation for some m1 mn, then these mi's will belong to the submodule generated by x1 up to xn for all I. Okay, this is like solving linear equations over modules. The module elements are in these submodules where they are located. So I have linear equation with coefficients. The coefficients form a m regular sequence. Then the elements in the module, which are coefficients of this linear equation, they are in the submodule generated by x1 up to xn. Okay, so you apply, most of the proofs are by induction. So apply induction on n. If n equal to 1, I have this equation. Yeah. So does it? How does it prove? X1 is M regular, so M1 is 0. So this is fine. Okay, so assume it for n minus 1. Assume the statement for x1 xn minus 1. Yeah, linear equation where the sequence is having length n minus 1. Okay. Yeah, but you see this x1 m1 plus xn mn equal to 0. Read this equation in m mod x1 xn minus 1n. If you do that, what happens?
X and mn bar is 0.
Yeah.
And xn is m by x1, x2, xn minus 1.
Right. If you read this equation, then xn mn bar is 0. But xn is a regular element on m mod x1 up to xn minus 1 m. So this says that mn belongs to the submodule generated by x1 up to xn minus 1. Yeah. So that means I have a formula mn equal to x1 n1 x2 n2 plus xn minus 1 nn minus. N was not a good choice. So I will just change it to n prime. Yeah. All right. So this is Mn is this. So go back to this equation that we started with and substitute. So I will get x1 m1 plus xn minus 1 mn minus 1 plus xn and substitute formula for mn x1 and let me not use primes. Okay, I will just change it to v1 x2 v2 plus xn minus 1 vn minus 1 where vi's are in m. Yeah. Now what can you do? Can anybody guess the next step?
Use the induction.
Yeah, but to apply induction, I must get a relation in n minus 1 elements, right?
So it's x1 into m1 plus xn v1.
Right. Just write it as an equation in x1 up to xn minus 1 with coefficients in the module. So this is x1 m1 minus xn vn v1 plus x2 m2 minus xn v2 and so on, right? The last one will be xn minus 1 mn minus 1 minus xn vn minus 1. This is 0. Now this is a relation involving, this is a linear equation where the coefficients x1 up to xn minus 1 are n minus 1 elements. This is a m sequence, and therefore by induction, these elements m1 minus xn v1 mn minus 1 minus xn vn minus 1, they are where are these elements? They are in this submodule. But these are multiples of xn. So that says that is m1, mn minus 1, they are in x1, xn, m. Okay? Yeah. So mn was already here. We already have information about mn, And now I derive the information about M1 up to n-1, and that finishes the proof. Is that clear? I think time is over, almost. How much time? 6 more minutes. Okay. Yeah. Yeah, I don't think I can finish the next theorem. So I will stop here and continue with the properties of M sequences. And next time I will do homological characterization. And using the homological characterization, we will derive many formulas about length of M sequences. Okay. And prove ultimately that maximum, all maximal M regular sequences over a local ring have same length, and that length is at most the dimension, crude dimension of the model. Okay. All right, so I'll stop here. Thank you.